Okay, let's dive into something that sounds like it's straight out of science fiction. We're going to start with a thought experiment. Picture this, a perfect vacuum. I mean, truly empty space, colder, more barren than the deepest voids between galaxies. Absolutely nothing there. Now, inside this perfect emptiness, we're going to place two mirrors. They're perfectly smooth, they're not electrically charged, and they're facing each other. There's no magnetism, no real gravity to speak of, and absolutely nothing in the space between them. So, your first thought is probably, well, nothing, right? They should just sit there forever. But that's not what happens at all. The mirrors, they get pushed together. A real, measurable force appears seemingly out of nowhere from the absolute emptiness of space. This is the Casimir effect, and honestly, it's one of the strangest and most profound discoveries in all of physics. So where on earth did this wild idea of a force from nowhere come from? This startling prediction was made way back in 1948 by a Dutch physicist named Hendrik Casimir. And the funny thing is, he reportedly stumbled upon this whole concept while working on something totally different, the properties of mayonnaise. Somehow that led him to this incredible insight that a vacuum isn't as empty as it looks. So what is going on here? How does this force just appear? To get our heads around it, we have to go deep into the quantum world and completely rethink what we mean by empty space. Turns out, according to quantum mechanics, a true perfect void doesn't actually exist. Yeah, the quantum vacuum isn't a void at all. It's more like a fizzing, bubbling soup of energy. At every single point in space, pairs of what we call virtual particles are constantly popping into existence and then annihilating each other almost instantly. It's this chaotic dance of energy that's happening everywhere all the time. It's the baseline energy of the universe itself. Okay, the best way to visualize this is to think of all that vacuum energy like waves in an open sea. In the ocean, you've got waves of every possible size, long, rolling ones and short, choppy ones. But now, imagine you place two big ships really close together. In that narrow gap between them, some of the longest waves just can't fit. They're excluded. And that's the key. You end up with more wave energy, more pressure on the outside of the ships than on the inside. And that pressure difference physically pushes the ships together. The Casimir plates are just like those ships, and the waves are those quantum vacuum fluctuations. So it's not a force pulling them together, it's the energy of the universe outside of them pushing them in.
But hold on, just when you think you've got the answer, there's a twist. Because while that vacuum energy explanation is the most popular one, it's not the only one. And this brings us to a bit of a debate, because physicists are still arguing about the true source of this mysterious force.
So the big question becomes, is this vacuum energy actually real? I mean, physically real. Is the vacuum really doing the pushing? Or could the effect actually be coming from the materials themselves? You know, this isn't a new debate. Even before Casimir made his prediction, the legendary physicist Wolfgang Pauli was deeply skeptical. He basically said in his Nobel lecture that this zero-point energy had no physical reality. He thought it was just a weird quirk in the math that physicists should probably ignore. And that same skepticism is at the heart of the main alternative theory today. Some physicists, like Robert Jaffe at MIT, argue that you can calculate the force without ever mentioning the vacuum. They suggest it's actually a super complex version of a van der Waals force. You know, the same kind of short-range force that lets geckos climb up walls. In this view, the attraction comes from tiny quantum fluctuations happening inside the atoms of the plates themselves, not from the empty space. Okay, so we've got two competing theories. How do we even know this force is real? Well, that's where we leave the chalkboard behind and head into the lab. Because here's the thing, regardless of what causes it, we are now absolutely certain that the Casimir force is real. Now, measuring this force was incredibly difficult. I mean, it's unbelievably tiny. For decades, experiments were just too imprecise. But then in 1997, almost 50 years after the prediction, a physicist named Steve Lamoureux finally nailed it. Using an incredibly sensitive setup, he measured the force between a sphere and a plate, and his results matched the theory almost perfectly. It was a huge breakthrough. And don't let its quantum origins fool you into thinking this force is weak. It's all about distance. While you'd never notice it in everyday life, if you bring two plates to within just 10 nanometers of each other, that's a gap about 100 atoms wide. The Casimir effect creates a pressure equal to 1 atmosphere. That's the same pressure the air around us exerts, but created from, well, nothing. And just when you think you've finally got a handle on it, the Casimir effect throws another curveball. It turns out the force isn't always attractive. By carefully choosing the materials and the liquid you put between them, you can actually make it push things apart. Scientists actually did this with a super clever setup. They took a gold object and a silica object and submerged them in a specific liquid. It all comes down to how these different materials interact with electric fields. With just the right combination, the quantum pressure imbalance flips on its head, creating a repulsive force strong enough to cause what's been called quantum levitation. It just opens up a whole new world of possibilities.
So what does this all mean for us? That brings us to the future of the force. This weird quantum push and pull isn't just a lab curiosity. No, it has some seriously profound implications. From the tiniest machines we can build, all the way up to the biggest mysteries of the entire cosmos.
At the tiniest scales, we could use repulsive forces to build frictionless nanomachines that never stick together. At the largest scales, understanding this vacuum energy could be the key to solving the cosmological constant problem, which is this huge disagreement between the energy theory predicts and what we actually see in the universe. Some physicists even think that if we can measure the Casimir effect with enough precision, we might just find evidence of hidden extra dimensions of space. So we started with a simple question about two mirrors in empty space, and we've ended up at the very frontiers of cosmology. It just goes to show you that sometimes the most profound secrets of the universe aren't hiding out in distant stars, but in the seemingly empty space that's all around us.